Hi, and welcome to my channel, and welcome back to Transmission Lines. In the first episode of Transmission Lines, we derived the telegraphers equations and discussed the connection between the electromagnetic fields and voltage and currents. Um, Here, to remind you, are the telegraphers equations in their full glory. We will start from them and derive the important results on wave propagation in transmission lines, the impedance of the transmission line, and the reflection coefficient. So let's see what's the corresponding wave equations for the telegrapher's equations. Applying the same technique we used before, taking the derivatives with respect to z and with respect to time to both equations, we get the wave equations for the voltage and currents. Note that we have the second derivative of v with respect to z and time, and we have L times c, which is related to the speed of the wave. Using the same technique, we get the second equations for the current, and these are the wave equations for the voltage and current. Note that the velocity is 1 over the square root of the L hat times C hat, which is the capacitance and inductance per unit length. But as we've seen previously, L hat times C hat is mu 0 times epsilon 0, which are constants of nature and are completely independent of the geometry of the transmission line. So the speed is only dependent on these constant. And what we have is that the speed of the propagation of the wave is related to the constant of nature, and this is actually the speed of light. So we get a relation between the speed of light and these constant. In the general case, when usually you have some insulating material between the conductors, the epsilon 0 needs to be changed to epsilon, and if you have some magnetic material, mu 0 needs to change to the actual permittivity of the material. Now, let's discuss a transmission line with a sinusoidal AC current injected at z equals 0. In other words, we drive currents which changes sinusoidally in time. I'm going to use the phasor technique for the time dependence, namely replacing the amplitude and phase of the current drive and the wave by a complex number whose magnitude is the magnitude of the drive or wave, and the phase is the phase of the wave relative to the drive. This is standard stuff you do in AC circuit analysis. We have an AC current running into the transmission line. The current and voltage are dependent only on Z, but the change in time is an implicit change by using the phasors. So as usual in phasors, the time derivative is replaced by minus j omega, where j is the square root of minus 1. Looking at the first telegrapher's equations, it becomes L times j omega times I. And the second telegrapher's equations becomes di over dz equals c hat j omega times v. Combining the two together and taking the second derivative of I with respect to z, we get that it is sine constant times the current, and we arrive at the equation of an harmonic oscillator in z. If you've seen the harmonic oscillator, you know that this is the form of the equation, the second derivative of of the function is some constant times the function. This equation is solved with two possible solutions, one with a plus and one with a minus. The relation between the constant in the exponent before the z is called the wave vector, and usually it's denoted by k. So you can see that k equals omega times square root of L hat times C hat. To summarize, we have two solutions, one with a plus and one with a minus. They are both valid. The plus solution is related to the forward propagating wave in the z direction, and the minus is relating to a backward propagating wave in the minus z direction. Now, if we want to go back to the expression without phasors, we get the form of the current wave explicitly with x and t. The relation between the velocity of the wave and the wave number and the angular frequency are given in these formulas. Note that we have two periods. We have the period in space and period in time. The period in time tau is important when you are sitting at a constant position and watching the wave go up and down. And the period in space is important when you take a snapshot of the wave at a fixed time and measure the distance between adjacent wave peaks. Okay, let's look at the full form of the wave and try to find what the relation between the voltage and the current are. Using the telegrapher's equations and substituting, we get that the change in the voltage with respect to z is just taking the derivative, namely multiplying by jk. And the derivative with respect to t is multiplying by a minus j omega. So we have the telegrapher's equation giving us a relation between the voltage amplitude and the current amplitude. And this is the relation between them, writing it more a little nicely. Using the fact that the wave velocity is what we've derived before, we find the ratio between the voltage and the current is related to the inductance and capacitance per unit length. The relation between them is that the voltage amplitude over the current amplitude, shown here by V naught over I naught, is simply the square root of the inductance per unit length over the capacitance per unit length. We call this ratio the impedance of the transmission line, usually termed by Z naught. Note that if the voltage and current are in phase, because we have an imaginary J factor on both sides, which means that they have the same phase. This means that the transmission line does not behave like a capacitor or inductor. It behaves like a resistor. You can extract power out of the source, and the transmission line behaves as an ohmic load as seen by the source. I've drawn here what the currents and voltages are doing during the propagation of the wave. So what you see here, the charges, or more accurately, the charge density on the conductor. And you have a wave with regions having more charge, of course, and you have the opposite charge on the inner conductor. When the wave is propagating, the charge density wave will be moving, and note that the current is highest, namely most positive, where we have the most density of charge, and the current is most negative when you have the negative charges moving. So here goes the wave and how it propagates. you can see that the voltage and current are in phase. You have a maximum voltage where you have a maximum current. And note that the movie is a bit misleading. Charges are not moving at the speed of light, of course. They are moving back and forth, creating a density wave, similar to a sound wave in the air. The charges interact with each other at the speed of light, but move at a much lower speed. Going back to traveling waves, we have two solutions, the forward traveling wave and the backward traveling wave. Suppose we inject some forward wave into the transmission line and suppose that we have a final length L. We don't place anything at the other end, the Z equals L. We just leave it open, namely infinite resistivity. At the edge of the transmission line, we would have a total current of 0, of course, because the current cannot get out of this transmission line. This means that the forward current and the backward currents must be identical. The current at Z equals L is 0, so we get this formula for the current over here. Just substitute L for Z. And we get the backward current is some phase factor times the forward current. So the phase between them just changes, but the ratio between the currents or the absolute value of the currents is equal to 1. They just change the relative phase between them. At the open end, Z equals L, the ratio of course is -1 because they have to cancel each other. And at the injection end, the forward and backward are equal but have a different phase. When you have two waves with equal magnitude going at opposite directions, you get a standing wave. Now let's look at the general case where we have two transmission lines, but they have different capacitance and inductance per unit length. The left side has L hat and C hat, and the right side has L prime hat and C prime hat. The current going forward is I sub F, and the current going backwards is I sub B. That's on the left side. On the right side of the transmission line, we have only forward current, I prime sub F, and the voltage at the interface is V. So let's do some algebra. The voltage at the left side of the interface is the sum of the forward wave and the backward wave, namely the voltage sum, and it's equal to the voltage on the other side, which is V prime forward. Using the relation between the impedance and the current and the voltage, we get this equation. And for the current, we just have that the total current is going into the interface and out of the interface should be identical because of charge conservation. So I forward minus I backwards is just I forward prime. Some of the current is reflected and some is transmitted. Now we have equations for the forward, backward, and transmitted current. If we combine these three equations and relating the forward and backward current, and of course the impedances, we can easily solve them and get the ratio between the forward and backward current. The ratio is called the reflection coefficients for obvious reasons. It's usually denoted by the letter gamma, and its value is given by this formula which relates the impedances of the different transmission lines and the reflection factor. Note that the impedances are exactly the same. We get no reflection, and it's obvious because it's the same transmission line. Also, if Z prime is infinity, we get the same formula as we got before. We get reflection coefficient 1. Note that if Z naught prime is 0, we get again a reflection coefficient which is 1. But if the impedance is 0, we get a minus 1 in gamma. And if it's infinity, we get a plus 1. If we have a short circuit here, we have the reflection with a sign change. You could put some load here instead of the transmission line, the right transmission line. Suppose the load is an impedance ZL. You'll get the same results, and so you have the reflection coefficients is related to the load and the impedance of the transmission line by the same famous formula. But this time, instead of a transmission line, you just have a load, which is usually termed ZL. Okay, let's see how much power is transmitted to the second transmission line. The reflection coefficient is gamma, and let's see how much power is going through the transmission line and how much power is reflected. The incoming power is just the impedance of the transmission line times the forward current square, and the reflected part is of course the same expression, but now it's the backward current squared. The transmitted power is the impedance Z0 prime times the forward current prime squared. Using all the formulas we had, we get the transmitted power is Z0 times I forward squared times 1 minus gamma squared, and it shows that we have energy conservation because the incoming power is just the sum of the reflected power and the transmitted power. Thanks for watching, and please remember to subscribe to see more videos on electromagnetism.